Automatic transmission.
An automatic transmission is a type of motor vehicle transmission that can automatically change gear ratios as the vehicle moves, freeing the driver from having to shift gears manually. Most automatic transmissions have a defined set of gear ranges, often with a parking pawl feature that locks the output shaft of the transmission stroke face to keep the vehicle from rolling either forward or backward. Similar but larger devices are also used for heavy-duty commercial and industrial vehicles and equipment. Some machines with limited speed ranges or fixed engine speeds, such as some forklifts and lawnmowers, only use a torque converter to provide a variable gearing of the engine to the wheels. Besides traditional automatic transmissions, there are also other types of automated transmissions, such as a continuously variable transmission, CVT, and semi-automatic transmissions, that free the driver from having to shift gears manually, by using the transmission's computer to change gear, if for example the driver were redlining the engine. Despite superficial similarity to other transmissions, automatic transmissions differ significantly in internal operation and driver's feel from semi-automatics and CVTs. A conventional automatic transmission uses a torque converter instead of a straight friction clutch to manage the connection between the transmission gearing and the engine. In contrast, a CVT uses a belt or other torque transmission scheme to allow an infinite number of gear ratios instead of a fixed number of gear ratios. A semi-automatic retains a clutch like a manual transmission, but controls the clutch through electrohydraulic means. A conventional manual transmission is frequently the base equipment in a car, with the option being an automated transmission such as a conventional automatic, semi-automatic, or CVT. The ability to shift gears manually, often via paddle shifters, can also be found on certain automated transmissions, manumatics such as Tiptronic, semi-automatics, BMW SMG, and CVTs, such as Lineatronic. The automatic transmission was invented in 1921 by Alfred Horner Munro of Regina, Saskatchewan, Canada, and patented under Canadian patent CA 235757 in 1923. Munro obtained UK patent GB 215669215,669 for his invention in 1924 and US patent 1,613,525 on January 4, 1927. Being a steam engineer, Munro designed his device to use compressed air rather than hydraulic fluid, and so it lacked power and never found commercial application. The first automatic transmission using hydraulic fluid was developed in 1932 by two Brazilian engineers, José Braz Araripe and Fernando Lely Lemos, and subsequently the prototype and plans were sold off to General Motors, who introduced it in the 1940 Oldsmobile as the Hydromatic transmission. They were incorporated into GM-built tanks during World War II and, after the war, GM marketed them as being battle-tested.
Comparison with manual transmission.
Most cars sold in North America since the 1950s have been available with an automatic transmission based on the fact that the three major American car manufacturers had started using automatics. Conversely, in Europe a manual gearbox is standard, with 20% of drivers opting for an automatic transmission. In some Asian markets and in Australia, automatic transmissions have become very popular since the 1990s. Vehicles equipped with automatic transmissions are not as complex to drive. Consequently, in some jurisdictions, drivers who have passed their driving test in a vehicle with an automatic transmission will not be licensed to drive a manual transmission vehicle. Conversely, a manual license will allow the driver to drive both manual and automatic vehicles. Examples of driving license restrictions are Croatia, Dominican Republic, Israel, United Kingdom, some states in Australia, France, Portugal, Latvia, Lebanon, Lithuania, Ireland, Belgium, Germany, the Netherlands, Sweden, Spain, Austria, Norway, Hungary, South Africa, Trinidad and Tobago, Belize, Japan, China, Hong Kong, Macau, Mauritius, South Korea, Romania, Singapore, Philippines, United Arab Emirates, Qatar, India, Estonia, Finland, Saudi Arabia, in March 2012, Switzerland, Slovenia, Republic of Ireland and New Zealand, restricted license only.
Automatic transmission modes.
Conventionally, in order to select the transmission operating mode, the driver moves a selection lever located either on the steering column or on the floor, as with a manual on the floor, except that most automatic selectors on the floor do not move in the same type of pattern as a manual lever. Most automatic levers only move vertically. In order to select modes, or to manually select specific gear ratios, the driver must push a button in, called the shift lock button, or pull the handle, only on column-mounted shifters, out. Some vehicles position selector buttons for each mode on the cockpit instead, freeing up space on the central console. Vehicles conforming to U.S. government standards must have the modes ordered PRNDL, left to right, top to bottom, or clockwise. Prior to this, quadrant-selected automatic transmissions often used a PNDL layout, or similar. Such a pattern led to a number of deaths and injuries owing to driver error causing unintentional gear selection, as well as the danger of having a selector, when worn, jump into reverse from low gear during engine braking maneuvers. Automatic transmissions have various modes depending on the model and make of the transmission. Some of the common modes include: as well as the above modes, there are also other modes, dependent on the manufacturer and model. Some examples include: some early GMs equipped with Hydra MATIC transmissions used S to indicate second gear, being the same as the 2 position on a Chrysler, shifting between only first and second gears. This would have been recommended for use on steep grades, or slippery roads like dirt, or ice, and limited to speeds under 40 miles per hour. L was used in some early GMs to indicate L, OW gear, being the same as the 2 position on a Chrysler, locking the transmission into first gear. This would have been recommended for use on steep grades, or slippery roads like dirt, or ice, and limited to speeds under 15 miles per hour.
Hydraulic automatic transmissions.
The predominant form of automatic transmission is hydraulically operated. Using a fluid coupling or torque converter, and a set of planetary gear sets to provide a range of gear ratios.
Parts and operation.
A hydraulic automatic transmission consists of the following parts. Torque converter, a type of fluid coupling, hydraulically connecting the engine to the transmission. It takes the place of a mechanical clutch, allowing the transmission to stay in gear and the engine to remain running while the vehicle is stationary, without stalling. A torque converter differs from a fluid coupling, in that it provides a variable amount of torque multiplication at low engine speeds, increasing breakaway acceleration. This is accomplished with a third member in the coupling assembly known as the stator, and by altering the shapes of the vanes inside the coupling in such a way as to curve the fluid's path into the stator. The stator captures the kinetic energy of the transmission fluid, in effect using the leftover force of it to enhance torque multiplication. Pump, not to be confused with the impeller inside the torque converter. The pump is typically a gear pump mounted between the torque converter and the planetary gear set. It draws transmission fluid from a sump and pressurizes it, which is needed for transmission components to operate. The input for the pump is connected to the torque converter housing, which in turn is bolted to the engine's flywheel, so the pump provides pressure whenever the engine is running and there is enough transmission fluid. Early automatic transmissions also had a rear pump, allowing push-starting, planetary gear set, a compound epicyclic planetary gear set, whose bands and clutches are actuated by hydraulic servos controlled by the valve body, providing 2 or more gear ratios. Not part of some manufacturers' transmissions during some eras, Honda being but 1, clutches and bands, to effect gear changes. One of 2 types of clutches or bands are used to hold a particular member of the planetary gear set motionless, while allowing another member to rotate, thereby transmitting torque and producing gear reductions or overdrive ratios. These clutches are actuated by the valve body, see below, their sequence controlled by the transmission's internal programming. Principally, A type of device known as a sprag or roller clutch is used for routine upshifts downshifts. Operating much as a ratchet, it transmits torque only in one direction, freewheeling or overrunning in the other. The advantage of this type of clutch is that it eliminates the sensitivity of timing a simultaneous clutch release apply on two planetaries, simply taking up the drivetrain load when actuated, and releasing automatically when the next gear's sprag clutch assumes the torque transfer. The bands come into play for manually selected gears, such as low range or reverse, and operate on the planetary drum's circumference. Bands are not applied when drive-overdrive range is selected, the torque being transmitted by the sprag clutches instead. Bands are used for braking. The GM Turbo Hydramatics incorporated this valve body, hydraulic control center that receives pressurized fluid from the main pump operated by the fluid coupling torque converter. The pressure coming from this pump is regulated and used to run a network of spring-loaded valves, check balls and servo pistons. The valves use the pump pressure and the pressure from a centrifugal governor on the output side, as well as hydraulic signals from the range selector valves and the throttle valve or modulator, to control which ratio is selected on the gear set. As the vehicle and engine change speed, the difference between the pressures changes, causing different sets of valves to open and close. The hydraulic pressure controlled by these valves drives the various clutch and brake band actuators, thereby controlling the operation of the planetary gear set to select the optimum gear ratio for the current operating conditions. However, in many modern automatic transmissions, the valves are controlled by electromechanical servos which are controlled by the Electronic Engine Control Unit, ECU, or a separate Transmission Control Unit, TCU, also known as Transmission Control Module, TCM, hydraulic and lubricating oil, called automatic transmission fluid, ATF. This component of the transmission provides lubrication, corrosion prevention, and a hydraulic medium to convey mechanical power, for the operation of the transmission. Primarily made from refined petroleum, and processed to provide properties that promote smooth power transmission and increase service life, the ATF is one of the few parts of the automatic transmission that needs routine service as the vehicle ages. The multitude of parts, along with the complex design of the valve body, originally made hydraulic automatic transmissions much more complicated, and expensive, to build and repair than manual transmissions. In most cars, except US family, luxury, sport utility vehicle, and minivan models, they have usually been extra cost options for this reason. Mass manufacturing and decades of improvement have reduced this cost gap.
Energy efficiency.
Hydraulic automatic transmissions were earlier almost always less energy efficient than manual transmissions due mainly to viscous and pumping losses, both in the torque converter and the hydraulic actuators. A relatively small amount of energy is required to pressurize the hydraulic control system, which uses fluid pressure to determine the correct shifting patterns and operate the various automatic clutch mechanisms. However, with technological development, some modern continuously variable transmission are more fuel efficient than their manual counterparts. Manual transmissions use a mechanical clutch to transmit torque, rather than a torque converter, thus avoiding the primary source of loss in an automatic transmission. Manual transmissions also avoid the power requirement of the hydraulic control system, by relying on the human muscle power of the vehicle operator to disengage the clutch and actuate the gear levers, and the mental power of the operator to make appropriate gear ratio selections. Thus the manual transmission requires very little engine power to function, with the main power consumption due to drag from the gear train being immersed in the lubricating oil of the gearbox. The on-road acceleration of an automatic transmission can occasionally exceed that of an otherwise identical vehicle equipped with a manual transmission in turbocharged diesel applications. Turbo boost is normally lost between gear changes in a manual, whereas in an automatic the accelerator pedal can remain fully depressed. This, however, is still largely dependent upon the number and optimal spacing of gear ratios for each unit, and whether or not the elimination of spool and accelerator liftoff represent a significant enough gain to counter the slightly higher power consumption of the automatic transmission itself.
History and improvements.
Modern automatic transmissions can trace their origins to an early horseless carriage gearbox that was developed in 1904 by the Sturtevant brothers of Boston, Massachusetts. This unit had two forward speeds, the ratio change being brought about by flyweights that were driven by the engine. At higher engine speeds, high gear was engaged. As the vehicle slowed down and engine RPM decreased, the gearbox would shift back to low. Unfortunately, the metallurgy of the time wasn't up to the task, and owing to the abruptness of the gear change, the transmission would often fail without warning. The next significant phase in the automatic transmission's development occurred in 1908 with the introduction of Henry Ford's remarkable Model T. The Model T, in addition to being cheap and reliable by the standards of the day, featured a simple, two-speed plus reverse planetary transmission whose operation was manually controlled by the driver using pedals. The pedals actuated the transmission's friction elements, bands and clutches, to select the desired gear. In some respects, this type of transmission was less demanding of the driver's skills than the contemporary, unsynchronized manual transmission, but still required that the driver know when to make a shift, as well as how to get the car off to a smooth start. In 1934, both REO and General Motors developed semi-automatic transmissions that were less difficult to operate than a fully manual unit. These designs, however, continued to use a clutch to engage the engine with the transmission. The General Motors unit, dubbed the automatic safety transmission, was notable in that it employed a power-shifting planetary gearbox that was hydraulically controlled and was sensitive to road speed, anticipating future development. Parallel to the development in the 1930s of an automatically shifting gearbox was Chrysler's work on adapting the fluid coupling to automotive use. Invented early in the 20th century, the fluid coupling was the answer to the question of how to avoid stalling the engine when the vehicle was stopped with the transmission in gear. Chrysler itself never used the fluid coupling with any of its automatic transmissions, but did use it in conjunction with a hybrid manual transmission called fluid drive, the similar HY drive used a torque converter. These developments in automatic gearbox and fluid coupling technology eventually culminated in the introduction in 1939 of the General Motors Hydra-Matic, the world's first mass-produced automatic transmission. Available as an option on 1940 Oldsmobiles and later Cadillacs, the Hydra-Matic combined a fluid coupling with 3 hydraulically controlled planetary gear sets to produce 4 forward speeds plus reverse. The transmission was sensitive to engine throttle position and road speed, producing fully automatic up and down shifting that varied according to operating conditions. The Hydra-Matic was subsequently adopted by Cadillac and Pontiac, and was sold to various other automakers, including Bentley, Hudson, Kaiser, Nash, and Rolls-Royce. It also found use during World War II in some military vehicles. From 1950 to 1954, Lincoln cars were also available with the Hydra-Matic. Mercedes-Benz subsequently devised a 4-speed fluid coupling transmission that was similar in principle to the Hydra-Matic, but of a different design. Interestingly, the original Hydra-Matic incorporated 2 features which are widely emulated in today's transmissions. The Hydra-Matic's ratio spread through the 4 gears produced excellent step-off, and acceleration in first, good spacing of intermediate gears, and the effect of an overdrive in fourth, by virtue of the low numerical rear axle ratio used in the vehicles of the time. In addition, in third and fourth gear, the fluid coupling only handled a portion of the engine's torque, resulting in a high degree of efficiency. In this respect, the transmission's behavior was similar to modern units incorporating a lock-up torque converter. In 1956, GM introduced the Jetaway Hydra-Matic, which was different in design than the older model. Addressing the issue of shift quality, which was an ongoing problem with the original Hydra-Matic, the new transmission utilized 2 fluid couplings, the primary one that linked the transmission to the engine, and a secondary one that replaced the clutch assembly that controlled the forward gear set in the original. The result was much smoother shifting, especially from first to second gear, but with a loss in efficiency and an increase in complexity. Another innovation for this new style Hydra-Matic was the appearance of a park position on the selector. The original Hydra-Matic, which continued in production until the mid-1960s, still used the reverse position for parking pawl engagement. The first torque converter automatic, Buick's Dynaflow, was introduced for the 1948 model year. It was followed by Packard's Ultramatic in mid-1949 and Chevrolet's Powerglide for the 1950 model year. Each of these transmissions had only 2 forward speeds, relying on the converter for additional torque multiplication. In the early 1950s, Borg-Warner developed a series of 3-speed torque converter automatics for American Motors, Ford Motor Company, Studebaker, and several other manufacturers in the US and other countries. Chrysler was late in developing its own true automatic, introducing the 2-speed torque converter Power Flight in 1953, and the 3-speed Torque Flight in 1956. The latter was the first to utilize the Simpson compound planetary gear set. General Motors produced multiple turbine torque converters from 1954 to 1961. These included the twin-turbine Dynaflow and the triple-turbine Turboglide transmissions. The shifting took place in the torque converter, rather than through pressure valves and changes in planetary gear connections. Each turbine was connected to the drive shaft through a different gear train. These phased from one ratio to another according to demand, rather than shifting. The Turboglide actually had 2 speed ratios in reverse, with one of the turbines rotating backwards. By the late 1960s, most of the fluid coupling 4-speed and 2-speed transmissions had disappeared in favor of 3-speed units with torque converters. Also around this time, whale oil was removed from automatic transmission fluid. By the early 1980s, these were being supplemented and eventually replaced by overdrive-equipped transmissions providing 4 or more forward speeds. Many transmissions also adopted the lock-up torque converter, a mechanical clutch locking the torque converter pump and turbine together to eliminate slip at cruising speed, to improve fuel economy. As computerized engine control units, ECUs, became more capable, much of the logic built into the transmission's valve body was offloaded to the ECU. Some manufacturers use a separate computer dedicated to the transmission called a Transmission Control Unit, TCU, also known as the Transmission Control Module, TCM, which share information with the engine management computer. In this case, solenoids turned on and off by the computer control shift patterns and gear ratios, rather than the spring-loaded valves in the valve body. This allows for more precise control of shift points, shift quality, lower shift times, and, on some newer cars, semi-automatic control, where the driver tells the computer when to shift. The result is an impressive combination of efficiency and smoothness. Some computers even identify the driver's style and adapt to best suit it. ZF Friedrichshafen and BMW were responsible for introducing the first 6-speed, the ZF 6 horsepower 26 in the 2002 BMW E65 7 Series. Mercedes-Benz's 7G-tronic was the first 7-speed in 2003, with Toyota introducing an 8-speed in 2007 on the Lexus LS 460. Derived from the 7G-tronic, Mercedes-Benz unveiled a semi-automatic transmission with the torque converter replaced with a wet multi-clutch called the AMG SpeedShift MCT. The 2014 Jeep Cherokee has the world's first 9-speed automatic transmission for a passenger vehicle to market.
Automatic transmission models.
Some of the best-known automatic transmission families include General Motors, Dynaflow, Powerglide, Turboglide, Turbo-Hydromatic TH350, TH400 and 700R4, 4L60E, 4L80E, Holden Tramatic, Ford, Cruise-O-Matic, C4, CD4E, C6, AOD OD, E4OD, ATX, Exod AX4S AX4N, Cummins 68RFE, fitted to the Ram diesel segment, Chrysler, TorqueFlite 727 in 904, A500, A518, 45RFE, 545RFE, Borg-Warner, later Aisin AW, ZF Friedrichshafen automatic transmissions, Mercedes-Benz transmissions, Allison transmission, Vuid Turbo, Aisin AW. Aisin AW is a Japanese automotive parts supplier, known for its automatic transmissions and navigation systems. Honda, Nissan Jatco, Volkswagen Group, O1M, Drivetrain Systems International, DSI, M93, M97 and M74 4-speeds, M78 and M79 6-speeds, Hyundai Powertech, 4F12, 4F16, 4F23 4-speeds, 5F25, 5F16, 5F23 5-speeds, 6F17, 6F26, 6F46 speeds, 8F40, 8F58 speeds, Mini Cooper, automatic or manual transmission, all models. Automatic transmission families are usually based on Ravignu, Lepeltier, or Simpson planetary gear sets. Each uses some arrangement of one or two central sun gears, and a ring gear, with differing arrangements of planet gears that surround the sun and mesh with a ring. An exception to this is the Honda-matic line from Honda, which uses sliding gears on parallel axes like a manual transmission without any planetary gear sets. Although the Honda is quite different from all other automatics, it is also quite different from an automated manual transmission, AMT. Many of the above AMTs exist in modified states, which were created by racing enthusiasts and their mechanics by systematically re-engineering the transmission to achieve higher levels of performance. These are known as performance transmissions. Example of manufacturers of high-performance transmissions are General Motors and Ford.
Continuously variable transmissions.
A fundamentally different type of automatic transmission is the continuously variable transmission or CVT, which can smoothly and steplessly alter its gear ratio by varying the diameter of a pair of belt or chain-linked pulleys, wheels or cones. Some continuously variable transmissions use a hydrostatic drive, consisting of a variable displacement pump and a hydraulic motor, to transmit power without gears. Some early forms, such as the Hall system, which dates back to 1896, used a fixed displacement pump and a variable displacement motor, and were designed to provide robust variable transmission for early commercial heavy motor vehicles. CVT designs are usually as fuel efficient as manual transmissions in city driving, but early designs lose efficiency as engine speed increases. A slightly different approach to CVT is the concept of toroidal CVT or infinitely variable transmission, IVT. These concepts provide zero and reverse gear ratios. Some current hybrid vehicles, notably those of Toyota, Lexus and Ford Motor Company, have an electronically controlled CVT, eCVT. In this system, the transmission has fixed gears, but the ratio of wheel speed to engine speed can be continuously varied by controlling the speed of the third input to a differential using an electric motor generator.
Manually controlled automatic transmissions.
Most automatic transmissions offer the driver a certain amount of manual control over the transmission's shifts, beyond the obvious selection of forward, reverse, or neutral. Those controls take several forms. Some automatic transmissions modified or designed specifically for drag racing may also incorporate a transmission brake, or trans brake, as part of a manual valve body. Activated by electrical solenoid control, a trans brake simultaneously engages the first and reverse gears, locking the transmission and preventing the input shaft from turning. This allows the driver of the car to raise the engine RPM against the resistance of the torque converter, then launch the car by simply releasing the trans brake switch.
Effects of automatic transmission on vehicle control.
Although an automatic transmission provides a superior driving comfort over a manual gearbox, in particular in a very dense traffic or in urban driving, where frequent gear changes are required, the intrinsically automatic logic of an automatic transmission can affect the attitude of a vehicle in marginal conditions, for example during cornering or in slippery road conditions. Since the shifting is proportional to the engine speed and accelerator input, the automatic transmission will tend to change gears even if not wanted by the driver. For example, When a vehicle with an automatic transmission descends downhill on a slippery road in a high gear without applying throttle, whereby vehicle's engine moderately decelerates the descent, an unwanted downshifting will effectively increase the resistance on the vehicle's drivetrain, eventually leading to an entire loss of the traction control over the vehicle with possible disastrous results.